So let's say that we have managed to do some quality control. We have a ground state geometry and everything. We are now working on the presentation of the reports. And one of the main reasons that I've worked on this QCAM program is that many times a non-theoretician will do a presentation that is not complete. That means that when you present theoretical results, you need to present enough information to for a specialist to assess the quality of the calculation. A simple fact: in many articles, you don't have the functional or the basis set function. So there is no such information. That means that a theoretician cannot redo the calculation and check. So when you do some calculations, or when you're working with a theoretician, you need to ask him such information. And when you read a paper, or when you want to do some calculations, remember always to give the software, okay, the functional. Here it's the number of basis function because it doesn't have the name, but the best is to put the name of the basis function. Okay? Here, in this case, the report goes further more because it will give the information of the grid size, if there is a solvent, what kind of thresholds were used for the convergence, how tight the convergence managed to get, how many excited states and what kind of excited states were computed. So we've computed 15 singlets and 15 triplets. Okay? And we have done a frequency calculation at room temperature. Because with the frequency calculation, we also have the entropy, free enthalpy, Gibbs energies. So that's why we need to know the temperature. We have in the following the results. The total molecular energy when you do some reactivity, if you want to compare reactants, products, transition states, for example. The HOMO number, that means that how many orbitals are doubly occupied and what is the number of your HOMO. The HOMO energy, LUMO energy, and there is the HOMO minus 1 and LUMO plus 1 to check if you have some generate states, for example. You have the convergence nuclear repulsion energy, if you want to compare the repulsion energy between two conformers and so on. Then we have some TDDFT calculations results, and I will follow them. But I want to finish with thermochemistry, number of negative frequencies, and the electronic and 0-point energy. So the 0-point energy is here. If you compare the total energy, the potential energy without vibrations, and you compare the energy of your first normal mode, vibrational states, this difference is called the 0-point energy. This energy, the lowest point in this curve, does not exist. Even at 0 kelvins, the molecules are in these vibrational states. So at 0 Kelvin, there is no freezing totally. There is everything in the lowest vibrational state possible. So this is the 0-point energy. And in the results, you have the information here. So if you compare the total energy here, so minus 29, 18, 49, for example, and here it's 0.1 artery above, the 0 point energy is 0.1. When you do the electronic and the thermal contribution of the energy at room temperature, you have a slightly higher energy, okay? And you can calculate the enthalpy, the Gibbs free energy, okay? So this one includes the entropy, and you have the entropy of your molecule. So this is more for thermochemistry and reactivity, depending if you have some bondings that are created or not. And then you have the table of the frequencies, most intense frequencies, if you want to compare with an ER table. Okay. Our main results for many of your problems are the absorption spectra. Okay. So we have a table here, and we found this information in the log file directly. I will show you. So you can open the TD. You can open the td.log, for example. So there is like 68,000 lines, okay? However, if we, I will show you briefly. What we have here is reading the geometry and the basis set, and is starting some SCF compounds calculations. However, the SCF is already computed, so in one cycle he has done the wave function. So now he has the wave function for the ground state, and he will start to optimize the excited states. So there is quite a lot of iterations, okay? It's an iterative process where he is looking for the 15 lowest in energy excited states that are perpendicular and correspond to the time-dependent Schrödinger equation with respect to the calculated ground state. So you see, for example, here that in the first approximation, the new state 1, S1, was the old S2, and he is mixing the states until he finds the correct one. So the geometry will change a little bit until he finds the best 15 first states. You can see that he is taking into account more than 15 states. Indeed, he has like 60 states in energy, but they are not fully calculated. Okay. So this is quite long. And in the end, if you start by the end, so this is the geometry, the charges, wave function. No, the best thing is to search for excited. Okay. Yep. So it's better. It's at one. It's line 1000. Okay. So if you have opened your td.log, you can have the information of the excited states at the line 1065. He has calculated a first excited state, that is a singlet, with an energy of 3.698 electron volt, or 335.27 nanometers. He has an oscillator strength. The oscillator strength is the probability of the absorption. That means that here the probability is really weak. Here the probability is 36%. It's quite strong. So first excited state is silent. That means that it does not show in the spectra. However, the second excited state is quite intense and is centered with this calculation at 258 nanometers. And then there is something that is 3% of probability, so much less, 0%, 0%, 0%, 12% at 212. So that is why when some experimentalists, when they comment an absorption spectra, you cannot say that the first band is S1, second band is S2, third band is S3. When they say that in the head, they are talking about the visible singlet or absorbing singlet states. So the first that absorb, the second that absorb, the third that absorb. And it's not for the first S1, S2 or S3. There is quite a lot of non-absorbing states, either by symmetry or by dipolar moment. I will explain the symmetry and dipolar moment. I've explained it last year, okay, but probably it's better if I do it again. But I will show you here with these results, okay? So another thing, the first excited states, many times the compounds, the experimentalists say it's homo-LUMO. Here you have the orbital 44 to 46. And 44 is HOMO minus 1, 46 is LUMO, so you have a good coefficient on the HOMO minus 1 LUMO. In the singlet 2, you have 45 to 46, but is not alone. You have more than one orbitals that are considered in the calculation. That does not mean that you have one electron from the orbital 44 that goes to 46 and one of the 44 that goes to the 50. It's not like that. The thing is, when you do a calculation, so here it's a diagram, just an example. When you say it's an orbital from the HOMO to the LUMO, you imply that the LUMO of your excited states has the same LUMO as your ground state. And sometimes not. That means that when you remove an electron here and it goes here, all the other electrons adapt. And here you have an electron where there were nothing, and it will generate a repulsion with the other electrons that are nearby. For example, here in this orbital that is a little bit centered on the center of your molecule, if you go to the LUMO plus 1, you will have the electron goes in the outer part of your compound. That means that here in the center, the other electron will say, yeah, less electron repulsion, whereas in the outer part, you have more electronic density going to this part, and that will generate more repulsion. So when you move an electron, even if in TDDFT you have vertical monoexcitations, that means that you have one electron that is moving at most, okay, and the atoms do not move. That does not mean that the electrons, the others, will stay identical. That means that the wave function of your excited states is not, or maybe does not have the same orbitals as the ground state. That means that when your electron goes to the LUMO plus 1, sometimes when it gets there, it's not the LUMO plus 1 anymore, it's the LUMO, or the LUMO plus 2. So to compensate, what you have in information is a linear combination of all the transitions that you need to take into account to have the correct density displacement. That means that here, to consider the second excited states, we need to take into account this majority, okay, that means HOMO-LUMO, a little bit of HOMO-LUMO plus 1, a little bit of HOMO minus 2 LUMO plus 1, and HOMO minus 2 LUMO. And if you consider this plus this minus this, you have, and squared, everything squared, you have the correct energetic or electronic displacement. That is why the density difference is probably the best approach. That means that you need not only to compare the orbitals, but to compare the density. Let me show you what kind of information we have. Okay, so here you have your HOMO, LUMO. Okay, so for example, if you have an HOMO that is quite centered in the bromine and there is nothing here, to the LUMO where there is nothing in the bromine and quite a lot here, you have the bromine as a donor, the carbonyl as an acceptor part, and you can, if you have an HOMO-LUMO part, like a donor acceptor part. HOMO minus 1 is more non-bonding electrons of the oxygen, slightly anti-bonding here. And the LUMO plus 1 is the anti-pi star orbital of only the bridge. So we can compute the energy differences. Okay? So for those who have the reports, you have those pictures. And here, how does it work? In blue is the electron gain. That means that you see that, for example, between S1 and S0, you have the benzene part that gains electrons, this carbon that gain electrons, and this is the losing part. That means that it's the non-bonding of the oxygen that lose electrons and give it to the pi system. Since between this non-bonding and the pi star there is an overlap that is really weak, you have a probability that is weak. To have a big probability, you need an overlap between the two, and you need to create a dipolar moment. And here, for example, in the second state, where we have HOMO, LUMO, and LUMO plus 1, we have the bromine that lose electrons. All these electrons, all these atoms lose density. So this is your electronic hole, and this is your electronic excitation, electronic excited electron. And you see that the barycenter of the negative of the hole is around here, and the barycenter of the excited electron is around here. So you have created a dipolar moment. You have a charge transfer, so this is good. And it is in the same pi orbital. So that means that here you have some overlap between the atoms. So you have quite a lot of overlap and a charge transfer. This transition is absorbing. You have the details in the table. For example, here you have the lambda. The lambda is the quantity of overlap between the wave function, initial wave function, and the end wave function. The dct and qct is the distance of charge transfer, and q is the quantity of charge transfer. That means that here you have a lot of electronic change, okay, but the dipolar moment will be okay. However, the overlap is quite weak. Here we have a good overlap and we have a large distance. So the dipolar moment that is a product of d by q is a large dipolar moment with a good overlap. And this is proportional to F. And then you have the electronic spectra, okay, absorption spectra in wavelengths and wave number. You have the pictures, but you have also the text files with all the points if you want to get this and compare with the experimental data. That means that you can get this curve, open it with Excel, or better another grapher like Origin, Sigmaplot, Matplotlib, and you can transfer this information here, the oscillator strengths. You can get the equivalent with a Gaussian broadening. That means that for each transition we consider a Gaussian form that is proportional to the oscillator strengths, and so you don't have the energy and the oscillator strengths depending on the energy. You have directly the molar absorptivity. And if you have a chiral compound, you have the circular dichroism. Okay. So you see in Gaussian you have the details in the log file of the energy, the wavelengths, and you have the linear combination of transition. So here you have one electronic transition that is a linear combination of of different excitations. And to understand the wave, the weight of the different excitations, you need to square. Okay, so that is why in your table, if you want to compare, you will see that between here it's HOMO -1 LUMO, okay, it's not 0.68 or 69, it's directly 94%. That means it's 0.69 squared. And you see that therefore the first excited state is mainly HOMO minus 1 LUMO, when the second state is HOMO LUMO. So if someone presents the graph and say here this is the HOMO LUMO, is correct, however it's not S1. So please try to not say that this is S1, this is S2, this is S3. You are forgetting non-absorbing states, excited states, and it's more complicated than that. If you do, for example, if you say it's HOMO LUMO plus 1, HOMO LUMO plus 2, it usually you will be wrong. To get the orbitals, you can create your orbitals with GabEdit, Avogadro. For example, in my report, the geometry is set automatically. Maybe you don't find the angle, the point of view has the best, so you can do your own orbitals. You can use GaussU, Avogadro, GabEdit, okay? To do your own Gaussian broadening, you have a Windows tool here that is free and it works well. It's coded by Noel Boyle and it's called GaussSum. It will read your datlog, your TD datlog, and it will create a spectra. So for example, it will create where is the UV spectra, okay? So you will have this, and it will create two outputs that are the UV spectrum that text and UV data. UV data is a table that you have in your report that tells you that each transition and the probability, and UV spectrum is this Gaussian with the same broadening. That means that you will have the possibility to get the information and to get it to be able to compare with the experimental data, for example. Okay, so now the look to
So with GaussSum we can make spectra out of our log file?
Yep.
Mm.
And you can choose the Gaussian broadening. That means your Gaussian, you set the width of your Gaussian at half maximum, and depending on your temperature of your system, maybe you can change a little bit the width of your Gaussian to match the experimental data. I've chosen by default a 3000 wave number, and usually it's quite enough, but maybe you can, for example, what you can do is to if you have clearly an experimental data where you have a full Gaussian, or what we can do is with the emission, and the emission part is really generally it's one Gaussian emission. You can calculate the width of your Gaussian, and you set this value as your Gaussian broadening width, and it will adapt your spectra with this parameter. It's quite easy. You download, it's a graphical interface. You open your TD log, it reads it, and you set your Gaussian width at the half maximum, and it generates the spectra.
To build this spectra with GaussSum, I've searched a file and then I have to find what SCF done.
No.
No.
You have to choose absorption spectra.
I have SCF done, K501, imaginary framework and custom.
What?
Uh,
Wait. Let me download the GaussView. Install Windows.
yeah, I've chosen all in one.
Download. Okay, so here you file open, you open your TD
log. Yeah.
Yeah, and you can select electronic transition.
Electronic transition.
Okay.
Okay.
And you select the limit of your graph, the number of points to generate,
okay,
and the full width at half maximum. So you see by default it's also 3000 wave number.
Why we need this value? Like FWHM.
Okay, like, so if you click, okay, let me see, maybe 300 is not enough. Let's put 200. Okay, so if you see here, in my calculation, we have, let's compare here. So the first excited states, let me get the both, if I can have both. Okay, perfect. The first excited states is at 335 nanometer, but the oscillator strength is super low, so you don't see it here. The first absorbing state is at 258 and is quite intense. It's this green bar. And yeah, okay. And then you have a 254 nanometer. It's much weaker. Is this one? And then we have a silent one, silent one, silent one, and then something at 212 here. But in reality, you don't have Dirac interactions. We don't have something that is at one wave number, because we have movement, because we have agitation, because we have thermal energy, and we have vibrational states that are coupled. One easy way to have a spectra that goes from a one transition to a band is to consider a Gaussian for each transition. That means that this one we have a Gaussian and it's proportional to f. So here the f being really small, the Gaussian is 0. Here we have a strong oscillator strength, and we will have a Gaussian that will represent that will be quite intense, and that will represent this strong absorption. And for each Gaussian, you need to define the central energy. So this one is easy, is your central, your excitation, okay? And you center your Gaussian, but you need to know what will be the half width of a Gaussian. A Gaussian function is defined as an exponential around a value. So this value is set here, and depending on the spreading of your Gaussian, and this is the full width at half maximum, okay? And that gives you the value that allows you to define the form of the Gaussian. And normally, in reality, it's not a real Gaussian, because it's something that is more complex, because it depends on the temperature It depends on the coupling of the vibrational forms. For example, if you have a naphthalene, you have not one peak, but several peaks for one excitation. And so this is something that is quite semi-empirical. It's an approximation. It works quite well. But for example, if you see that your theoretical computed spectra is too narrow, you can augment the half width and full width at half maximum, and that means that your Gaussian will be wider, but he will go lower, and the integral of your Gaussian will always be the same and depends only on the oscillator strength. That means that, for example, this, if we generate the same one, let's try. If we do a 6000, this is your corresponding spectra. You see, this one is wider, and it's so wide that now it goes in this part. And so now this, better if we start with 100. Okay, and 3000. So here you have the same computed data, but this is a computed data with 3000 wave number as a full width at the half of the maximum, when here it's 6000. So depending on your experimental data, maybe 3000 is too narrow, or maybe 6000 is too wide, depending. Okay?
Okay, so I don't have any theoretical concerns in order to choose this value. I have to make it empirically with linked to my previous knowledge, or maybe to my experimental data.
Exactly. And please, if you can indicate when you do this kind of treatment, if you don't use, for example, 3000, please indicate the value of your FWHM.
Okay.
Perfect. So now, officially, you can generate your orbitals. You can maybe I can show you one way. I think that I have Avogadro. Yep. So GaussSum works the same. To get the orbitals, you need to open the FCHK. MO. Avogadro. GaussView. GaussEdit. So on. Use the opt.fchk. So the FCHK is something of it's a binary file. It's something like the log file, but for the machine. There is more information in the FCHK. Let me download one and show you.
Monsieur?
Oui.
Nous, dans les fichiers que vous nous avez envoyés, on n'a pas de fichier .log en fait.
You don't have it. What is CRT? No. What is the acronym of your compound?
Oui. Des PP.
CTR. I don't understand. What are the files that you don't have? Because I see all the files here.
The log.
The td.log? Because I see the td.log. Maybe you don't see the .log because in Windows sometimes it doesn't show the extension. So if you have a file that is only td, beware that maybe in Windows it's the td.log because it knows that you can open it in some file. So depending on your Windows configuration, because you have the td.log. If you use Notepad to open an FCHK, you will find that this is something that you can read, but there is no words. So it's only for the machine. But there is in this file the information to draw the orbitals. So this is the opt.fchk that you must use with Avogadro, GabEdit or GaussSum to open and see the orbitals. And you can check if it's the same in if you have the same values as the report, if you have a report.
I opened in Avogadro,
Yeah.
and I see only the orbitals and the structure, but not the other things that you mentioned.
Okay. So, but for those who didn't open, you can, for example, click in the HOMO and you will see the orbital. And you can check, for example, you don't have the pictures for the LUMO plus 4, 6, and so on. So you can check on those orbitals if you want to use this information. So td.log with GaussSum to have the spectra. Avogadro and GaussSum and GabEdit with the opt.fchk for the molecular orbital. However, if you don't have the report to generate the energy, the density difference is quite complex and it's quite tricky.
Have to render every time an orbital in Avogadro.
There is by default only the -4 and +4 that are already set and rendered, and so if you want more, yes, you need to compute them. There is some computation.
Mm-hmm. And why +4 and -4 are by default?
It's arbitrary. For example, in the report, I only do -1 and +1 just for the reactivity. but maybe for excited states it's interesting to know the levels that are a little below and a little higher in energy, but how much? I think that they've set to -4 and +4. That means that it's 10 orbitals, and if you want more, you need to pay the price of computation. But it's not heavy.
The case is I don't understand actually what we get with this homo +1, homo -1, homo -2. What data we get?
Yeah. So let's take the example for the bromobenzaldehyde and open with the TD. Okay. So if you've used GaussSum, you can open the in your directory. You have now a GaussSum 3 directory, and you have a file that is called UV data.
GaussSum directory in program files?
No, in your file where there is the td.log.
Okay. Yes, UV data.
If you open the UV data, you have the excitations in a table, okay, with the energy, the wavelengths, the oscillator strength, the symmetry, if it's a singlet, a triplet, and the transition. So for the first excited states, it's an HOMO -1 to LUMO at 95%. Okay? So if you want to understand this transition, you can picture the HOMO -1. So here, let me up. So we have this orbital that is quite centered in the CO part and mainly in the oxygen part. There is nothing here. And it goes to the LUMO part. That is a pi star like that. So if you take the two pictures, you can draw an arrow saying that the electron was there and now is here. And for example, the second orbital, the second transition is 89% is HOMO-LUMO. So you draw the picture of HOMO to LUMO, and now you can understand, for example, here there is a lot. Now there is few here, so there is more here. So there is an electronic displacement from the bromine to the carbonyl. Okay?
Okay, and why we have different colors here for them? I know that it is like different signs, but what is the nature of it?
It's a phase. Let's see. The electronic density is like how do we say that in English? Okay. It's like a cover, okay? So you have something that covers a surface, but it's not flat. There is high and lows, okay?
Okay.
And it's not the quantity of the electron, huh? It's the wave function has sign changes, and it's sometimes they do a comparison with the drumming instrument, where you have the oscillating surface that provoke the sound, and the most let me find this energy. Wave function science drumming kit. No. Okay. Perfect. Oh, Wikipedia. So the first excited, for example, 1s orbital is this, and you can imagine if it was faster. This changing is what a drumming kit is doing. When you make the fundamental sound of a drumming kit, the surface is oscillating from high to low and is provoking sound. But you can have more than one sound with the same drumming kit, and you can have an excited vibration when half of the surface goes up when the other goes down. And this is why in some wave function you have electronic density to the left, to the right, and no electron density to the center. That means that your wave function is oscillating between one up and one down. There will be always one up and one down, never two up and two down. So in the middle, the value of your altitude of your height is always 0. That means that your wave function is 0. That means your density is 0. There is no electron here. And to understand it, it's better to understand the electron as a wave. That means it's an electronic cover where you have electron density here, and no electrons here. And it can oscillate from a sine or a phase, and this is the sign of your wave function. So here, in this case, I'd like to have I would like to have a background that is white, please. Okay. And maybe well, okay. So what do we see here? We have a p orbital, because in the same atom we have two signs, and this is a p orbital, and this is also a p orbital, and here the two signs are opposing, blue, red. That means that here we have an anti-bonding interaction between this atom and this atom. It's also a change in sign. We have above green, red, blue versus blue, red. That means that between this carbon and this carbon, it's anti-bonding. Here, between the two here and the two here, we have blue and blue, and they overlap. So here we have a bonding interaction between the two carbon. Here we have an anti-bonding, anti-bonding, bonding, anti-bonding. So the property of the LUMO is an electron density, is an electron that is in a p overlap with some bonding and anti-bonding depending on the atoms pair. If you compare with the HOMO, we have also a pi type orbital, but now we have still anti-bonding here, but this time is bonding, bonding, anti-bonding, anti-bonding, bonding, bonding, bonding. So for example, you can see that if you go from HOMO to LUMO, here you lose those two bondings and two bondings, because now there are two anti-bonding, but you gain here two bonding. Since you lose 4 bonding and you have now 4 anti-bonding, and you increase only of 2 bonding, it's not interesting in terms of energy. You go higher in energy, but they are in the same kind of space. That is why between this and this you have a huge overlap. You have some electronic displacement, because here you have a lot of electrons here and nothing almost here, to few here and quite a lot here. So the electron barycenter is shifting, so we have a change, an electronic displacement during the transition. So we have a dipolar moment that is generated during the transition, and this is good. And we have also a good overlap, because there is all this part here where there is density in both cases. There is sometimes a change of sign, but there is quite a good overlap in this part. So that is why the HOMO-LUMO in this case is quite absorbing.
Okay, so we have changes in electron density and its localizations on atoms, but actually why for molecule, why it changes every time this localization, and how do we know, like we know that this HOMO-LUMO, we have them like simultaneous now. So like how we have them, all of them in one time.
I didn't follow. Your question is, how do we get all the orbital in just one calculation?
How we have it like in real life, or maybe like why exists so much HOMOs and LUMOs, and how like one LUMO and another LUMO, they can be like very difficult. How are they like living together in one molecule?
In chemistry, we have in organic chemistry there is not a lot of type of atoms. However, the same carbon, depending in the surrounding, will not have the same properties, and this is because the electron density is shared and can go, or is impacted to an extent that is just not the first neighbor. It's also many times the first neighbor of the first neighbor. That means that in terms of combinatorial, is like a Lego game, but we have a huge capability of making combinations that are unique, and therefore the electron density will be unique, and so for each time you will have HOMO and LUMOs that are different in energy and in forms. And for similar compounds you will have similar LUMOs, but if you have for example distinct chemical functions, you will have totally distinct frontier orbitals. Moreover, the HOMO is the highest electrons in energy, that means the most reactive, and the LUMO the lowest vacancy, the lowest unoccupied molecular. That means if you want to add an electron, it will go to the LUMO. So this is the most reactive acidic part, and with just changing the surrounding, you can change the energy levels. So it's quite fantastic because with few Lego pieces we can generate an infinite game. And if you do a Lego where you have a donor part and an acceptor part, and you change the bridge, you can kill the communication. That means that the donor property, the HOMO, is located on one part and the LUMO on another part. But if you change the bridge between the two, the electrons will communicate and you will have some interplay between the two, and it's almost an infinite ocean of possibilities.
Yeah, I understand for different molecules, but here we are talking about one molecule with like very many possibilities of HOMOs and LUMOs.
No, there is only one HOMO and only one LUMO.
Okay, but like LUMO plus one, LUMO plus two, and
those are higher in energy.
Mm-hmm.
And you can, for example, this LUMO plus 4 is a positive energy. For example, the LUMO plus 8 is at 1.2 electron volts. If you give the energy to send an electron from the HOMO to the LUMO plus 8, in reality, this electron will leave the molecule and go elsewhere, because there is here if you, for example, if you give him -7, that means if you give him 7.7 electron volts, the electron goes to almost 0. So you can reach something that is around LUMO plus 2, LUMO plus 3. But if you give him 1 electron more, he will directly probably ionize, and you will lose the electron and it will go to another molecule. So theoretically, we have a huge number of orbitals, but those are higher energy states with electrons in 4s, 5s, 7s, and those are never occupied in reality. They are just a mathematical expression of something that could be possible, but that in reality does not really occur. However, the HOMO minus are all existing functions. For example, if you are here in the HOMO minus 44, it's really a low energy, and this corresponds to the 1s of your bromine. And then you have the 2s of your bromine, 1s of your oxygen, 1s of your carbons, etc., etc. So here, here it's 1s, 2s bromine, 2p of bromine, 3s bromine, 2p bromine. So, and then we have the 1s oxygen, etc. So those are, there is quite a lot of HOMO minus something, but those exist. They are occupied orbitals and they correspond to core electrons, and then valence electrons, but are lower in energy because they are in a more, for example, the sigma bonds. The sigma bonds are more stable in energy than the pi bonds. So the orbital describing the sigma bonds of the valence shell is lower in energy than the highest energy, that usually are non-bonding atoms or pi delocalized orbitals, for example.
Okay.
Okay, So now we have the basics of quality control, and I would like you will have questions in the examen, and I would like in your oral presentation that you show me that you've checked on your compounds. You have in your oral presentation, you have to present me the computational strategy, functional, basis set. Explain to me that you understand what are the choices that we've made, are they adapted, and if there is a difference between the experimental data, maybe we can discuss on how much depends on the computational strategy, how much depends on the experimental errors. Okay? We now can generate your own spectra. You can understand and describe your excitations, and this is only the absorption part. You can generate your orbitals, and if you have the reports, you have the electronic density differences. Now the question is, you need to assess the quality of the calculation compared to the experimental data, and tell me if we need to calculate emission spectra with the same properties, or and so on. Okay, so I will shut down the recording for today, and I will leave. I will stay connected for half an hour. So if you know that you need some calculations, you can tell me, or you send me a mail. And if you want to work in group, you can separate and go to different groups. I will, by the way, make another group. And another group. Okay, so if you want, you can separate and go in different groups, and you can activate your screen sharing. You can talk together, and I stay around, and you told me, oh, it seems to be okay. We would like to have the emission spectra, and I think that we need to optimize the state 1, the state 2. Maybe we need some. Okay, and you can tell me if something is wrong. If what do you think we can do to have better things, or what could happen? Okay.